Yeah, okay. All right. Welcome everyone to our DSG seminar. It's my great pleasure to host Thomas Neumann. First, before I guess I introduce Thomas, let me, as usual, thank SAP for sponsoring this seminar series. So Thomas is a full professor at the Department of Computer Science at Technical University of Munich in Germany, where he has been since 2010. Prior to Munich, he was a senior researcher at Max Planck Institute for Informatics in Saarbrücken, and he holds a PhD from University of Mannheim. Thomas, without any doubt, is one of the most renowned systems researchers in our field, and he is known uniquely as one of the few researchers who also design, architect, and implement the systems he does research on. And instead of quick research prototypes, he implements production quality systems over very long periods of time. And his notable systems include RDF3X, which introduced many techniques, query processing and optimization techniques to manage RDF datasets, Hyper, which pioneered the technique of query compilation, and Hyper's Flash-based successor, Umbra. Hyper has been acquired, as many of you know, by Tableau, has been turned into a successful commercial company. And Hyper and Umbra today represent the state of the art in terms of performance in database management systems. So his research has been recognized by many awards. I can't list all of them, but I'll just mention his VLDB Test of Time Award and ICD 10-year Influential Paper Award for his work on the Hyper system, and the Gottfried Wilhelm Leibniz Prize, which is the most prestigious research award in Germany. So without further ado, let me thank Thomas for joining us and leave the floor to him. Thank you.
Thanks for the introduction. So today I would like to talk about adaptive join optimization with using search-based linearization. This is joint work with Bernhard Ratzke, one of my PhD students. So basically, what is our problem that we want to tackle? Classical join ordering. So we are given a query and we know that the query is on a declarative form. So here we say like we want to join 3 tables and we somehow have to find out how to do this. So this sounds easy. Problem is join ordering is, so joins in general are commutative and associative. So I have many choices how to do this. Here we see some variants. I can join A, B, C, or A with B and C, or B with A with C, and so on. And the problem is, the order matters. So if I choose a different join order, I can easily affect runtime by orders of magnitude. And finding the best order is, in fact, an NP-hard problem. Now, we know how to solve this problem, for example, using dynamic programming. So this gives me the optimal answer. The problem is that this does not scale to very large queries. And some of the queries can be very large, in particular if they're generated. So not human written, but if a machine has generated them, they can be very large. And this is the problem. And I want to talk about this today. Yeah, so now coming back to the original problem. So what we want to solve in join ordering is we are given a query as input, and then we want to construct the execution plan, and we do this over the query graph. So which means we look at all the relations, so they form the nodes in my graph. And then when I have a join predicate between 2 relations, I have an edge. So this describes the query graph. And this describes all ways I can construct a join, basically. Yeah, so my problem is, therefore, given a query graph, how to construct the execution plan. And as I mentioned before, in principle, we know how to do this. So this is a solved problem, because what we can do is we can simply use dynamic programming. Was pioneered by Sillinger et al. Already in 1979. And this told us how to find the optimal answer. Now, since 1979, a lot of things have happened. So we found much better algorithms than the original one. Like we can do not only lefty plans, but bushy plans. There are graph-aware algorithms, so which exploit the structure of the query. Therefore, it's more efficient if the structure is nice, and we can solve non-inner joins too, and all kinds of things. But at the end of the day, in worst case, we have exponential runtime. Now, there are some cases that are better, but in worst case, we're exponential. And this means that we can only solve this exactly for relatively small queries. Yeah, and this becomes a problem when we have generated queries, because some of these business intelligence tools generate really large queries. And of course, we must do something with them. Yeah, so we must tackle them. And so this is, so they said small queries are solved. For this kind of queries, yeah, query is 50 relations. So we start having problems, because if I just use a vanilla DP algorithm, this will probably not finish. That's too difficult already. And so what can we do? So then some people say, just use some greedy heuristic or so. But this is very unpleasant because then you have no guarantee about the result quality. And if you look at the plot on the right, so this shows you the distribution of costs compared to plans. So how frequent are costs plans with a certain cost normalized to the best cost? And you see that there are quite a few bad plans out there, and they can be bad with orders of magnitude bad. So really, really bad. And if you run a greedy heuristic, you have no guarantee at all. And what's even more unpleasant is it happens suddenly. So you get a good plan until you cross over some threshold, then you switch to greedy heuristics, and then terrible things happen. And this is clearly bad. And what's even worse is this is not by far the size of this query is by far not the end of the spectrum. We can get even larger queries. So we can get this kind of monsters here. So there's data by Tableau. They looked at the distribution of queries in their customer workloads. And they said here, benchmarks don't represent the real world. So they said it's quite common to have queries that touch a few hundred relations. So this can happen. And we must do something with this. And then there was a report by SAP that says the largest real world query that they saw touched nearly 5,000 relations. And clearly this is a problem. And if you look to the right, you see the optimization time of different systems, because this is currently recorded. I cannot tell you who DBMS A and B is. You can ask me in private, but let's say these are commercial database systems, and then there's Postgres. But independent of which system you use, at some point, these systems tend to become have real problems with query size. So they have a very high optimization time, and basically they are unusable for certain sizes of queries. So this is a challenge we want to tackle. Okay, and so for this we propose to use adaptive optimization. So the big picture for this works like this. First, we look at the query, and most say there's a long tail with large queries, but most of the queries are relatively easy. So therefore, the first question is this an easy query? And if the answer is yes, just solve it optimally. And most of the time, it will be the case. Then, is this a medium-sized query? And of course, we will talk in a moment what medium-sized means. But then we say we use search space linearization. I will also explain what this is. And then we will find not guaranteed optimal, but usually close to optimal query for this. And only for the really huge monsters, then we have to introduce some greedy component. But even this, we want to do in a graceful manner so that we don't fall off a cliff and get a terrible result, but that we can gracefully become more greedy as the problem becomes too large. Okay, so this is basically our strategy. And for performance reasons, also for correctness reasons, we don't consider cross products, at least not in the beginning. I will say a bit more about cross products later. First, we say we do queries without cross products. Okay, so now how do we find out if my query is difficult or hard? We see here some example numbers on the complexity of a query depending on the structure. You see, if you have a chain query, so one relation is joined to the next and so on, this is actually a polynomial problem. We can solve this in n to the power of 3, and the dB table is the size of n squared. Now, while we have a click query, complex is the thing is exponential, so 3 to the power of n, and dB size is also 2 to the power of n. And real queries are between these extremes. So chain query is best, click query is worst. And predict the runtime is a bit difficult, but what we can relatively easily compute is the size of the dB table. And this indirectly tells me how long the runtime is. Okay, so therefore we analyze the query graph structure to count the number of dB table entries that we will get. There was a Sigma paper that does this. And then we can predict how long the execution time will be. Okay, and if this size of the dB table is small, then we just run it. And so this is the small query case. So if we have up to 10,000 dB table entries, we say this is easy, we just solve it. What this means in practice depends on the query. For a chain query, for example, this means up to 100 relations, which is quite a lot. So this is best case. Worst case, click queries, 14 relations is threshold, less than 14. Real world query somewhere in the middle. So but in this range, we can just solve this exactly with the hypergraph-based DP from 2008, which adapts to the query graph structure and gives me the optimal answer with minimal runtime, at least minimal for all DP-based algorithms. So this algorithm is provable optimal. Okay, so this gives me a quick answer for small queries. Now, for the things that are larger than this, we have to do something. And how bad it is depends on the structure of the query graph. I said with a chain query, I can easily do 100 relations. For other queries, I cannot. Yeah, and so therefore, the chain query is linear in structure. Others are not. And now the tricks that we do is we make all problems linear. So this is what we call search-based linearization. So we make it linear, and then we can solve it very well. Now the question, of course, is how do we do this? And now, if you have a query like this, so we're joining R1 with 2, 2 to 3, 3 to 4, and so on. This is my query graph. Assume that we would know what the relative order of relation would be in the optimal plan. Of course, in reality, we don't know this, but assume we would know this. Yes, we would know in the final plan, the order would be this. So first 2, then 1, then 3, then 5, then 6, and 4. If this would be the relative order. So if we would know this, then we could construct the optimal join tree in polynomial time. And we do this by running a DP on this linear order, and we construct subchains of increasing size. So we say, first we take 2 tables, like 2 and 1, which gives me a small join tree. Then we take 1 and 3, gives me another join tree. And in this case, actually, 1 and 3 is, yeah, so no, is a crossproducts. We don't do this. But we nevertheless, we can consider this, compute the cost, and we make larger and larger trees out of this. And so then we get 2, 1, 3, and then we get 5 and 6, and this gives me a join tree, and we construct a larger tree, and so on. We build a small, deep dynamic programming algorithm on this, on increasing size. Okay, and in the end, we end up with, for example, this tree. I made this up. Of course, the shape depends on the cost, but we can compute this in polynomial time. Because the only thing we do is we consider associativity and not commutativity. And because we assume the relative order is known. Okay.
So can I ask you a question? So first, you're gonna take questions. Can we interrupt you during the talk?
Yeah, sure.
So what does it mean for the order? For like, why is like you gave an order example R2, R1, R3, R5, but why isn't not? Yes. Look at this tree, for example. Why is the order not R5, R6, R4, and then R2, R1? Like, what does order mean to you in a bushy plan, for example?
Of course, I did not tell you yet how to come up with this order. So, but I want to do this, and I will talk in a moment why we decide to do 2, 1, 3. I didn't tell this yet. I just say, if you would know by some oracle, some magical component will tell you that in the final plan, in the bushy plan, the relative order from left to right is 2, 1, 3, 5, 6, 4. If you would know this somehow, then we can reconstruct the optimal and the true optimal tree in polynomial time, because you just run dynamic programming over the size of the subchain, and you build larger trains from this. This gives you the true optimal result if you choose the leaf nodes correct. Of course, you're right. The question is, why did I choose 2, 1, 3 and not something else? I didn't tell you this yet. So I just say I have an oracle component that tells me this is the relative order, but does not tell me the structure. The structure, I don't know. The structure I construct with dynamic programming. So just the relative order I have to somehow get. And of course, the problem is that ultimately we don't know the optimal order. Yeah, but we make use of another algorithm. Yeah, so how do you know the order? Yeah, so we make use of an algorithm, namely of this one here. This is the so-called EKKBZ algorithm from TOTS and VLDB. And what this algorithm does, it gives me the optimal left deep plan in n square runtime. This is, and we know that this is indeed optimal. It has some constraints. First, it only gives me the left deep plan and not the bushy plan. And it has some constraints on how the query must look like. But the thing is, this has a low runtime and gives me a pretty good result. Yeah, in fact, with some fine print, it's optimal for left deep plans, not for bushy, of course, but for left deep plans, it's optimal. And then we take this as a good relative order, and then we run DP to construct a bushy plan from this. To say, okay, in which order should we really do this? So this is basically our oracle that we use for seeding. Yeah, and so what the EKKBZ algorithm does, it takes the query graphs and then construct a precedence graph. So this describe which relation has to come first, and then builds a linear order from this. Now, fine print, first we need a cost function that is okay, and then we need that the query graph is acyclic. If the query graph has cycles, then we construct a minimum spanning tree to make it acyclic, which of course is a heuristic step. So it could be that this was wrong. But we construct an acyclic query graph, and then we look at all the nodes and we assign a rank to them. A rank is basically the cost-benefit ratio. So running a join costs you something, but you get rid of tuples, which is good. Yeah, so and then you compute the ratio between selectivity and cost, 1 minus selectivity and cost, and this is the rank. And this tells me, okay, how beneficial is this join basically? And then what the algorithm does, it sorts on elements by rank, following the constraints by the precedence graph. I show you an example in a moment how this works. But basically, we look at all the joins, and then we try to sort them by rank. And sometimes this is not possible because I would like to do a join, but I cannot. This we call a contradictory sequence, and then we merge them into a single node. I will show you in a moment how this works.
Just another, can I ask another question? So the MST is you just take the weight of each edge if the join edge in the query graph as 1.
We take the most selective. We take so if I have a cyclic query, we only consider the most selective join edges. So you run a minimum spanning tree on the selective edges.
So you give weight.
But note that this is only for the oracle that gives me the relative order. We still run the DP on the full graph. So the dynamic programming does everything. But for the oracle that guesses the linear order, we consider only the most selective joins. So that says, okay, this is probably what we should do. Okay, and then here's an example. So this is my query. I want to join A with B, B with C, C with D, B with E, and then E with F. And then from this, I construct a precedence graph. Here, we have to do this for all relations, but I will only show you one, namely the one that starts with A. And then the precedence graph says, okay, if I start with A, next I can do B, and after B, I can do either E or C. I have a choice. I can join with any of these two. And then when I have E, I can F, and I have C, I can have D. And you see this blue number next to this. This is the rank, so the cost-benefit ratio. And you compute this by looking at the selectivities of the joins and the cost function. So you can look it up in the original algorithm, but basically we compute the cost and the selectivity, the ratio of these two. And this gives me the rank. Okay, and then here we see that, oh, we have a contradiction here. Namely, we would like to join with F before we join with E, because the rank of F is lower than the rank of E. But we cannot, because the join with F is infeasible because we need an attribute from E. Okay, so and therefore, if this happens, then we call this a contradictory sequence, and we know we can actually prove this, that in the final result, E must come directly in front of F. Okay, therefore we collapse them into one. Now we no longer have contradictions, so we can join this. So we merge these two lists by sort order, and this gives me, we merge them, and this gives me this list. So we say the linear order is A, B, C, E, F, D for this example. Okay, and so basically we do this for all relations and choose the cheapest one. And this is what EKKBZ does. And this is a provable optimal with a number of handprints, but only lefty plan, so only linear order. Okay, but this we use as a seed for the dynamic programming, and then we construct a bushy tree from this. So this is basically, this we use for medium-sized queries. Note, we can no longer guarantee optimality, of course. The only thing we know is we are at least as good as the best lefty plan. We cannot guarantee optimality for bushy plans, but in practice, it works pretty well. Okay, yeah, so this is the strategy. So we linearize using EKKBZ, then build the best bushy plan for that linearization. So good thing is we have a cubic runtime, and we are at least as good as the optimal lefty plan. So this is we can guarantee. And what we also know is that if our linearization was the best order, this we cannot guarantee, unfortunately. But if it was the best order, we are guaranteed to find the optimal bushy plan. So we we have a chance to be truly optimal with this algorithm. And we know that we are at least as good as the best lefty plan. And the runtime, of course, is good. So it's polynomial runtime. Okay, so this is for the medium-sized queries. So small DP, medium size, do this. But at some point, even cubic becomes too expensive, because even if n is large enough, even n to the power of 3 hurts you. Okay, and then we pull another trick out of the hat, namely we run iterative dynamic programming. So basically, we first choose a join tree using a greedy algorithm, and for this we use greedy operator ordering. So it's an algorithm from Leonidas Figaras, and this gives you a usually pretty decent plan, but of course it's a greedy heuristic, so it can be bad. And then we look at this plan and we take the most expensive subtree of size k and solve this with dynamic programming, so with linearized dynamic programming. So this idea comes from Donald Kosman and from Stotz 2000. But when he proposed it, he used a pretty slow DP algorithm, and therefore he could only use k equals to 7, which means you do a small polishing, but you cannot do a lot. But if you use this linearization thing, we can choose k equals to 100, so which means we can overrule the greedy step quite a bit. So we can take a large part of the query and then refine this with linearized dynamic programming to correct mistakes that the greedy step did. Okay, so in this we do it for the huge monsters. Of course, queries of this size are rare, but we still have to be able to run this. And this gives me pretty good results. Okay, now what does this mean in combination? So we see easy cases, we just solve, no problem. Then for the medium-sized cases, we get near optimal plans for common cases. I didn't give you quality results, I will do this later, but I can tell you that this linearization is usually close to optimal as far as we can. Sometimes we don't know, but as far as we know, it's close to optimal. And even for the large ones, we can no longer guarantee optimality, but in practice, it works very well. And optimization time is very low. So this here is the optimization time now with up to 1,000 queries. And this is really, really quick. Okay, so this was the first thing that we did. We called this linearized DP. And this worked, but we still had issues when we started. Actually, we had two problems. First, what do we do if we don't have such a nice query graph? Because so far I only showed you pleasant looking query graphs, so one edge between two relations, but there can be unpleasant query graphs with hyperedges. So edges that connect more than two relations. That's bad. Another problem is, what do we do with cross products? Usually we don't want this, but sometimes we do. And so in this, we tackled in a generalization of this that we called LinDP++ that extends this algorithm for these two cases. Okay, and so first, why do we need non-regular edges? Yeah, sorry.
Sorry, I have a question. Just more of a clarification question. So when you're doing this optimization, you are still relying on things like estimates of cardinalities and selectivities and things like that, right? I mean, you still don't know for sure what the exact values are, right?
Yes.
Okay. All right.
Of course.
So I guess a follow-up question is, when you do the greedy part and then, for the more difficult parts, you actually apply, the more extensive optimization, which is, I think, what you just talked about. You said that you get, near optimal, but that still relies on having fairly correct estimates of things like cardinalities and so on.
Yeah, of course. This is the usual thing of people who do query optimizers. We mean query optimal given our estimates. Yeah, so we can prove that if my model is right, I construct the optimal plan. Of course, in reality, model is wrong, and we all know this. But nevertheless, the absolute number that we construct is usually totally wrong, but we use this to compare plans, because in reality I don't care that much that I know how expensive this plan is. I only want to know if this is the best plan, or at least a good plan. And for this, the estimates tend to work okay. So if you look at the absolute number of what I predict how many tuples will come be after 20 joins, yeah, so this is totally wrong. But if you want to decide, is this order better than the other order, this tends to be okay. And actually, closer to the bottom, our estimates actually are usually somewhat accurate. And there also, this is what this polishing phase does. It looks at a subtree from the bottom, of course, and that's expensive and optimizes this. That this part, usually my estimates are still somewhat reasonable.
Right.
But you are right, of course, the estimates in general are the Achilles heel of this thing. So this is the largest problem that we have, how to get good estimates. Yeah?
Right.
So, but
okay.
here in this talk here, I don't talk about this at all. I just pretend as if I would have good estimates. So I just talk about because even independent of the optimization problem, optimization is hard. So even if I would have an oracle that gives me always a correct estimate, this is still an NP hard problem. So that estimation is an orthogonal. It's important, but it's an orthogonal issue. So here we just pretend that I know what's going on.
Okay, great, thanks.
Okay, and yeah, so then we generalize this to other problems. So first, why do we do this? Yeah, because it's not that rare. Yeah, so if you have a non-inner join, so like an outer join, for example, or semi-join, anti-join, this happens. And so we got a trace here from customer data from Tableau where they look at this, and that say that 20% of the queries involved an outer join. So outer joins are actually quite common. And they have outer join queries with up to 247 outer joins in a single query. So this is large. And so also other people reported that outer joins are common. And yeah, so we have to do something with them. And unfortunately, outer joins are not reorderable. So we cannot pick arbitrary orders and still get the correct result. So we have to be careful. And we can express this using hyperedges. And you see an example now. So here is an example secret query. They're saying A full outer join, and then comes B, C, and D, and these are inner joins. So these are regular joins. If we just look at the query graph, so who joins with whom, you would think that the query graphs look like this. A joins to D, D to B, B to C. Okay, but this is misleading because if you just trace the structure, we might end up with joins that are wrong. So like this is correct. So this is a correct join tree. We're joining A full outer join with subjoin. Okay, this is correct. If you look at this example here, this also follows the query graph because we're joining A to D and then to B and then to C, but this is actually wrong. It gives me a wrong result. You're not allowed to do this outer join before the inner joins. Inner joins must come first. Okay, and we can recognize this. We can look at the original query and see that we cannot reorder them. So these are reordering constraints. And we can express this in the query graph. So we say, oh, this is not permitted. And we can say you are only allowed to do the join with A when you have already joined B, C, and D. Okay, so this gives you an hyperedge, edge that connects A with B, C, D. Okay, and this correctly describes the outer join, the semantic of the outer join, but it's a problem because my algorithm cannot handle this. So the EKKBZ algorithm doesn't know anything about hyperedges, just assumes you have nice regular edges between relations. Okay, yeah, so this is a problem here. So how do we linearize my search space if I have this kind of edge? Note that for small queries is not a problem because the DP can handle these edges. So this works. But for the larger queries, we have a problem here. Okay, so therefore the question is, can we extend EKKBZ to give me linearization for hypergraphs? So graphs that connect more than two relations. Okay, and clearly, since I'm talking about this, it's possible. And basically what we do is we define a precedence graph for hyperedges. So here in this example, we have an hyperedge between, an hyperedge that connects C and D with E. Okay, so this is my hyperedge. So this is one big hyperedge. And we treat this differently depending on which direction you come. So we call this a forward or backward edge. So if you start with B, so you come from the left to this edge, then we call this a backward edge. We say during the merge phase, when you have B, you can join either with C or with D, no problem. But you are only allowed to join with E after you have already joined with both D and C. Okay, so you need both, and only then you can do this. And we can express this as an extra edge here. So this dotted edge means we have the special dependency edge, and this says, okay, the merge with E can only happen after both of the others are there. Okay, so this is relative minor change to the algorithm is not a big thing. Just during merging, we must delay a merge. Okay, but what happens if we come from the other direction? So if we, so with this we call a forward edge. So if we start with E, then there simply is no left deep plan. It's infeasible to construct a left deep plan for this edge. And therefore, what we do instead is we say we have this group here, C and D, and we find a linearization for this independently. So recursively, we solve this and we say, okay, the best linearization of this group is CBD, for example. Depends on the selectivity, of course, but we say we have CBD, we collapse this into one node, and then comes A and F. Okay, and this again looks nice for the EKKZ algorithm, and we can solve this, and we find the optimal order for this. Okay, so basically we use the recursion to construct a compound, so a group that captures all three relations. Okay, and so the guarantee that we can get again is the final plan is as good as the best left deep plan if there is a left deep plan. Now, for some queries, there simply doesn't exist one. It has to be Boucher. Then we cannot guarantee optimality, but in practice, it works pretty well. Okay, so this I have already claimed repeatedly. Now I want to give you some numbers to talk about this. And the interesting thing about optimality is, how do I know how good an algorithm is if my problem is really large? For the small ones, of course, I know because dynamic programming is guaranteed to be optimal. But if I have 40 joins, I usually cannot guarantee optimality. Okay, therefore, what we did is we implemented 10 different join algorithms, ran all of them, and checked what is the best result we could find. And this we defined then as optimal, or rather, we look at how much worse are we compared to the best known plan. And for the small queries, this includes DP results, and this is guaranteed to be optimal. For the large ones, of course, yeah, we just know we are the best of whatever we have seen. Okay, so therefore we ran this 10 algorithms, time out 1 minute. Note that the standard benchmarks are totally uninteresting here because they are too small. So TPCH, I think 6 joins is the maximum. There's nothing. And TPCDS also has a low number. We can easily optimize this. So you always find the optimal answer. Therefore, to stress this, we generate here random tree queries, realistic random tree queries. Realistic means most edges are key from key edges, a few non-key from key edges. And then with plausible shapes of different size, and then we ran this and compared different algorithms. How does this look like? Okay, and so here is a normalized cost, again, normalized to the best known plan. For the small queries, this means normalized to the true optimum, because we know the true optimum. For the large queries, we don't know, but it's the best we could find. And so we are comparing here just linearized DP with this ++ variant. Note that many of these queries contain non-inner joins, and this means that the linearized DP has to fall back to a greedy component. And because the original algorithm could not handle non-inner joins, so we had to use a greedy component and use DP for regular DP for small polishing, which means often we got poor results. So here normalized costs are between 1 and more than 10. So often we got poor results just because the greedy component killed me. Now, while if I include this non-inner edges in the EKKBZ step, I'm virtually always the best algorithm. Not truly always, sometimes somebody else finds a better plan, but in nearly all cases we are the best algorithm that is known. So it's, again, for the small queries, I can guarantee that it's truly optimal. For the large queries, I cannot, but it's the best that we know. Okay, so this constructs clearly very superior plans. Next question is, how much does it cost me? Because algorithm, of course, is a bit more complicated than if you have to handle this non-regular edges. But if you compare the cost, the difference is very small. So the runtime is nearly the same as if you would not consider non-inner edges. And also the absolute optimization time is not too high. So the 100 queries we can do in 80 milliseconds or so. I mean, after all, running the query also costs something. So therefore, this is reasonable optimization time. Okay. But there's still one thing that I had mentioned as limitation that we did not tackle yet. And this is, what do you do with cross products? So most of the time, we do not want to consider cross products. Yeah. Why? If you do consider cross product, your search space explodes. Because then basically every query is a click query. And after all, if you allow cross products, everybody can join with everybody. Yeah, so you don't want this because it's too expensive. And also the runtime of cross products is usually terrible, because we know that if you do A cross B, my runtime will be size of A times size of B. So why should I do this? Except if they are very small. So usually we don't want this, but if they are very small, we might want to. And another reason why we do not want to consider cross products usually, at least not out of the box, is if you have non-inner joins, a cross product can lead to a wrong result. So here's an example. So if we have our query from the beginning, we're joining A with BCD, we can build such a join tree just fine. But if we would allow cross products and we are not careful, we could, for example, do something like this. So we do this here, we do a cross between A and C. Yeah, after all, I can cross everybody with everybody, but this is clearly wrong. So this gives me a wrong result. Don't do this. Therefore, we have to be careful. We cannot just say, consider arbitrary pairs of relations for cross products. This is dangerous if you have non-inner joins. Okay, so therefore we have to be careful with this. So how do we tackle these both problems, search space explosion and correctness problems? We do this. Yeah, this would be allowed. So sorry, I didn't explain this. So cross between A and C is forbidden, but cross between C and D, for example, would be allowed. So we don't have to forbid all cross products, but some are okay, some are forbidden, and we have to figure out which one is okay and which one is forbidden. Okay, and we tackle this by so first, why do we want to tackle this? So observation is that sometimes cross products are a good idea. Usually they're not, but sometimes they are. For example, TPC-DS. If you do allow cross products in TPC-DS, you can improve the geometric mean by 15%. Yeah, and of course, yeah, we would like to do this. On the other hand, 82% of the queries do not benefit at all from cross products in TPC-DS. Okay, so therefore, what we would like to do is we only want to consider some cross products, and ideally just the ones that are important for performance, and the rest we ignore. Yeah, so this is what we want to do. Yeah, but how do we discover the valid ones and the important ones? So, and we do this by looking at our query graph, and intuitively we say a cross product makes sense if it allows me to avoid a large intermediate result. For example, here we have 3 tables, a big fact table with 10 million entries, and 2 dimension tables with just 10 and 4 elements. And of course, we can join them, but then we will do 2 times a join with 10 million. Yeah, and what we could do instead is we could say, okay, let's take this and sorry, I went too far, and just build a cross between D1 and D2. It's just 40 tuples, and this we join. Okay, so therefore we look at my query graph and I check, can I bypass expensive join by building a local cross? Okay, here we see joining F with D1 is 10 million and then another 10 million. Doesn't matter what I do, I always get 10 million. But if I would do a cross, then I would do a 40 and then 10 million. So which basically saves me producing roughly 10 million intermediate results. So this is cheaper because I can bypass this big fact table. Okay, and so when I look at my query graph, I check for such a situation where I have neighboring tables that are themselves small and that allow me to bypass plans. And while doing so, I can, because here I see if I have a non-inner join on this path, or if they're all inner joins. And I only do this, of course, if I have nice inner joins. Okay, so my rule here is if the cross product is smaller than both intermediate results, I add an explicit edge to my query graph. So I say, oh, this edge here would be a candidate 2. Okay, so I can consider this during dynamic programming. And then I can consider taking this edge if it makes sense. Could be that I still don't want to do this, but I give the algorithms a chance to consider this algorithm. Okay, now how much does it help? So here we check the improvement compared to no cross products. Here say if we do all cross products for 3 different benchmarks, TPCDS, LDBC, and joint order benchmark, of course, for most queries, no difference. So don't benefit, but some do benefit up to factor 13 or so. So there is a benefit for some queries. And now if I include all cross products, this is expensive to compute. But if I only use this heuristic of checking if we have neighboring entries which help, this is nearly as good. Yeah, for TPCDS and LDBC, I find everything. For joint order benchmark, I miss a few, but the really important cases I still get. Okay, so then I find the cases where cross products really make a difference. And the runtime or the optimization overhead of doing so is modest. Like if you just look at the topmost lines, this tells you how much more expensive does it get if I add these extra edges. For the linearized DP, the overhead is a few percent, so nearly nothing. If I do this in the DP phase, can become more expensive, but still it's not too bad. While if I would do this, if we would consider all cross products, my optimization time explodes. So 200 times optimization time. So this is not feasible, basically. It's too expensive. But considering some cross product edges is possible, and we get most of the relevant cross products. So this seems like an attractive trade-off between optimization time and quality of the result. Okay, so to conclude, joint ordering in general is a super important problem and very hard, unfortunately, as NP hard. And now we know most queries in reality are small, fortunately, so we can solve them exactly. Yeah, but some can be very large, and we must do the appropriate thing. So for the medium-sized queries, we can still find near optimal solutions with linearized DP. For the really huge monsters, yeah, we are lucky if you find a plan at all, but still we can, with low time, we can produce quite good plans. And we can generalize this even to non-inner joins and cross products, which is pretty nice because this allows me basically to tackle all kinds of queries. So, and then just one final word at the end. So the problem is NP hard, if we know this, but this doesn't mean much because in practice, we can solve virtually all queries either optimally or near optimally. So NP hardness is a bit misleading. So you shouldn't give up just because the problem is NP hard, because people don't give you click queries. They give you more reasonable queries in practice. And this you can solve reasonably well, even for very large queries. Okay, thank you.
Great. Thank you very much, Thomas. So we have a lot of time for questions. So please unmute yourself and you can pose questions to Thomas. Right, then maybe let me start. So I have a question. So in general, when you get a very large query like this, like that motivated this work, maybe with like 1,000, how many of them are primary foreign key joins that are not joining? And if I told you all of them are primary foreign key joins that are not growing, so it's not many-to-many relationships, for example, how many, from your experience, how frequent is that versus joins that were not that were growing, the intermediate sizes? And if I told you that they're all primary foreign key joins, does that change, and would that change any of the algorithms you use? Could that be exploitable?
So first, the good news is most joins are key from key joins, but most, unfortunately, is not all. There are non-key foreign key joins in there, even in TPCH, which is a pretty simple benchmark. Even there, you have, I think, 1 or 2 queries with non-primary key foreign key joins. And also in the real-world queries that we looked at, most queries are key foreign key joins, no questions. But there's a certain percentage of non-key foreign key joins that also growing joins do exist, and we have to cope with them. Yeah, so, and if I would know that none of my joins are growing, I think this does not really help me. I mean, where it does help me is in the quality of the estimates. because I can estimate the result of a join much better if it's a key for a key join. So I get much better result estimates. But otherwise, from an optimization perspective, it does not really help me. So the problem is just as difficult as if I would have growing joins. So it doesn't help, unfortunately.
Okay. Is there a question?
Yeah, actually, I'll go ahead. I have a couple of questions. By the way, my name is Arun. So one question is this, right? So you plotted, trees and you said about optimality. So just to be clear, you are estimating the cost of a given plan. So, and that's what you are using as a comparison point, right? So when you say one tree is better than the other, you are talking about its estimated execution cost, correct?
Yes.
Okay, so now is that of your area of interest? Did you take the next step and run the query and see how that correlates with the actual execution time?
Yes, I did. No, not for this huge monster queries because it's infeasible to no, but we played with this. For example, for the smaller things like TPCH, we can use an oracle, which means we run all possible join trees, really run them, because then we have no estimation error, and we check what happens then. Yeah, so it's interesting to look at. In small queries, you can do this. You can compare estimate with reality. And for the big monsters, we cannot because the space explodes. But yes. By the way, in general, I'm super interested in getting better estimates or doing other things like at runtime noticing, oh, it was wrong and recovering and this kind of stuff. So I'm not saying this optimization as I talked today solves all problems. So definitely we have a problem with estimation and we must tackle this problem. But
sure, and yeah,
independent of this, we must do something.
Yeah, sure. And I think the one next thing that did you try this? Like one straightforward thing to do is to publish a benchmark. I mean, take TPCH, maybe not it's old. Maybe take TPCDS, and see what kind of numbers you get. Right? I mean, choose your DBMS. Yes, choose your algorithm, and see what kind of numbers come out. Right?
Oh, this we did.
So okay, so and then can you report some good numbers? Like, did you get good benchmarking numbers?
Oh yes, yeah. So we construct very good plans with this, also compared to other systems.
Okay.
Yeah.
Okay.
So I think if in the this was a Sigma paper. In the Sigma paper, we also report TPCS numbers, I believe. If not, I can send you results, but I think it's included in the paper.
Sure. Yeah. And actually, maybe one or two other questions. So next is, okay, so it's good to talk about this 1,000 table queries. What is your take on can somebody write 1,000 table queries? I mean, first of all, can somebody make a sense of 1,000 table queries, leave alone 4,000 table queries? I mean, does it even, can humans actually comprehend?
So the 4,000 query, by the way, this is an absolute outlier. Yeah, so I only know a single query of this size. Yeah, nobody does this.
No, actually, even I would say, to forget about 4,000, even 50 tables. Like even 50 table queries. Can humans comprehend 50 table queries?
This is actually not rare. 50 table queries are not rare, and these are machine generated, of course. Yeah, so this is not no human wrote this by hand. So there is this. So I got data from Tableau, which does this business intelligence stuff, and they automatically generate queries of this size. And what happens typically is that they compute something like they aggregate data in a certain way, which can of course be already subquery, and then they aggregate the data in a different way, and then they join the results and this kind of stuff. So they touch the same data items multiple times in different angles, and then they combine the results with joins in a fully automatic manner. And you easily end up with 50 joins.
Yeah. Okay. So I think most of these large queries are machine generated. Fine. In that case, my next question would be one very sort of a repeating pattern that is observed is snowflakes, right? So you have a big fact table and then you have many dimension tables which are the spokes. Now those kind of queries can easily give you large table counts. So essentially PKFK queries, right? And then you have a bunch of other such combinations. So that's one common pattern. So in your work, did you sort of concentrate on that pattern, which is very common, right?
Yeah. We ran experiments, of course, with snowflakes and trees in general and those things, because you're right, this is a common structure. And of course, we want to handle this. But my original motivation for all this here was I want a join algorithm that can handle everything. Of course, I cannot guarantee optimality at some point, but at least I want to run this stupid query. Yeah, so because what should not happen is you give me a SQL statement and I cannot run because my optimizer doesn't finish. Yeah, so I need an optimizer that gives me a reasonable plan for an arbitrary query. So this was basically the challenge. Optimal would be great, of course, but reasonable is the minimum that I want.
So and actually, so I think along those lines. So one of the, I think I forget which paper, but I think one of the papers found something like in some cases it is much more beneficial to join the dimension tables first and then fact tables, and many optimizers cannot get that. So anyway, so your algorithms can get the idea of joining the dimension tables first.
This is exactly the case that you see here. This is in fact one fact table with 2 dimension tables. Yeah, so this is exactly the reason why we looked at cross products, because it can happen that you really want to consider these and not do the fact table.
Let me maybe take this offline, and because I think there might be a couple more people who want to ask questions. I think Ken wants to ask a question, and Arun, if there is time, you could continue.
Sure, yeah.
Because we have a bit more time. Yeah. Am I correct, Ken? Because you turned your video on. I assumed
I did turn my video on. That was. Am I audible, Thomas?
Yes.
Yeah. Okay. I just back to this kind of estimation question. So I understand that estimation is sort of not the problem that you're focusing on here. Is it orthogonal to what you're doing? Like, does the way that you do the search in this space kind of affect how much you're impacted by bad estimations? Do you know what I'm asking?
Yeah, you're saying if
like, for example, you may hurt yourself less with bad estimates if they're kind of later, if you do those joins kind of later in the plan than earlier in the plan.
Yeah. I see what you get.
Yeah.
Yes. In fact, of course, this page, in particular, this individual page here, for a regular joint ordering, of course, we have estimation errors, but everybody has estimation errors. We just do the best that we can. But for cross products, it's particularly dangerous, because if we would be wrong here, so then really terrible things can happen. Therefore, we are extra careful on this. This slide is very high level, but for base tables, we tend to have pretty accurate estimates. So even if we have predicates on this, our estimates are pretty good. We have a little error, therefore we are confident in this. Now, if this would be computed, so it could be intermediate subqueries, then our confidence is much less. Yeah, so then it could be that we have a large estimation error, and then we would not do this because we consider it's too dangerous. Yeah, because if I believe it's 1 tuple and already it's 10,000 tuples, this is a disaster if you do a cross product. Yeah, so therefore, in the cross product case, we have to check how confident we are that this is indeed true. Yeah, so you should only do this if you think, yes, this is right. And for base tables, we have pretty good estimates.
So you're saying that the algorithm that you're using now for cross products, you're kind of aware of the risks of. Oh, okay.
Yeah, because we have to add this cross product opportunity explicitly, and you should only do this if you are confident that your estimates are good. Sometimes you are confident even for subqueries, like if you bind the primary keys and there's only single tuples, then of course we are confident. Okay. But if there's uncertainty, you should not do this. It's too dangerous.
And does this, just one more thing, and then I'll let other people talk. So does this also affect the way you do this kind of linearization for the medium-sized queries?
No, in this case, we really only depend on selectivities. I wouldn't know. I think in general, it's an interesting idea to think about confidence. So how confident are you in the estimates? I think this is useful, but for linearization, I wouldn't know immediately how to make use of this.
Yeah, I don't know either. I just thought, I just know whether you thought about it or not.
Yeah.
So, okay.
So here I know how to do this, but for the other case, I don't know yet how to make use of this.
Okay. Okay. Cool. Thanks.
We have time for another question. Anyone? So I can ask one more question. So are there techniques, or have you considered techniques that take the query and maybe it's a large query, and I'll commit to joining a part of that join graph. And so I'll just reduce it to a single node, and I'll say, just take this as, I think you were kind of doing it in the linearization, or the one algorithm from like 1986 that you showed was doing something like that, joining E and F together and whatnot. But also in the DP phase, are there approaches that says it's a very large query, 100 tables or 1,000 tables, I'll just reduce it to 50 by committing to certain subgraphs within this join graph, and there'll be like these super nodes, and then I'll do DP on those. Are there approaches like this?
Yeah, this is the idea actually of iterative dynamic programming. You can formulate this in different ways, but this is one spin of the problem is, if you really implement this, is you see this is not that as cheap as either. So on a board, so if you draw this as a human, say, yeah, I just collapse this two and then, but if you really code this, you see, oh, this is not so super cheap to do, because finding the proper node to collapse is already expensive. Yeah, so which 50 nodes should I collapse? Yeah, so this is not so easy to do. But in fact, this is one part of our strategy for the really large queries. Yeah, so we get an initial structure with greedy ordering, and then we take important nodes, collapse them into one, run iterative DP on this, and then leave it as it is. So we say we don't touch this anymore. This is now a pseudo relation for us. And then we continue optimization with the rest. So this is actually the strategy that we run for the really large queries.
I think Amin has I'll let Amin have the last word. He turned his camera on.
So one last question, which is, have you considered when it comes to these large queries, picking a subgraph query that generates the least intermediate results, which then gets materialized, and then you kind of intermittently sort of computing or progressively optimizing, as opposed to optimizing everything and then executing everything?
This is definitely also a good idea. I played with this already a few years ago when I was visiting Microsoft. I was in the Microsoft SQL Server team as visiting researcher, and we played with this idea. Then just, if it's small, just run it, and then yeah, because then there's no uncertainty. You just see this is definitely also, you still have the problem. How do you choose your first plan? So before you run anything, how do you pick the initial plan? So therefore, it is in a way a bit an orthogonal question, because we must start somehow. But definitely just running a query and looking at the result is an attractive idea, because then there's no uncertainty. So I have seen the data.
Okay, thanks.
All right. Thank you very much, Thomas. Let's thank Thomas for this excellent seminar.